Hi, my name is Ziyan. I am a PhD student in the ECE department at Texas A&M University. I am presenting our work, Improved Sample Complexity Bounds for Distributionally Robust Reinforcement Learning. This is a joint work with Kishan Panaganti and my advisor, Dr. Dilip Kalathil. The goal of reinforcement learning is for the agent to learn a policy, which is a mapping from states to actions that maximizes the expected cumulative reward over time. Reinforcement learning has shown great successes in many areas. For example, AlphaGo's success in defeating a world-class Go player demonstrated the remarkable potential of reinforcement learning. Go is one of the most complex games humans ever created. Combined with techniques like Monte Carlo tree search, the reinforcement learning algorithm was able to surpass human expertise in a complex game. So much so that short after, the only worthy opponent is itself. There are many other examples of exciting real-world challenges that are tackled by reinforcement learning. However, most RL successes are due to problems being very structured, or tasks and environments can be well simulated. It is usually assumed that the testing environment is identical to the training environment. But in reality, the training environment can be different from the real-world dynamics. It can be due to the evolution of the real world or erroneous approximation of the real-world system. This is called the sim-to-real gap. In this talk, we focus on the robust Markov decision process, or RMDP framework. A finite horizon RMDP is a 5-tuple. We consider the tabular setting, that is, the state and action spaces are finite sets. H is the horizon length. We assume the reward functions are non-stationary, known, and deterministic. P0 is the non-stationary nominal models. We use this to define the uncertainty set, which is a set product of all measures close enough to the nominal model. This construction also ensures a property called SA rectangularity. Essentially, the worst model at each HSA pair is independent from those at other time states and actions. For more details, please refer to Iyinger's paper on RMDP. D as a distance is chosen as the Wasserstein metric and the three other F divergences, TV, chi-square, and KL. Rho is the robustness parameter that measures the size of the uncertainty set. The objective of robust MDP is to find the policy that performs the best under the worst model, hence the max-mean formulation. And the performance metric is the usual expected cumulative reward. We can further express this using value functions. We define the non-robust value function as the following. For any policy, its robust value is the expected cumulative reward taken with respect to the worst model P in the uncertainty set. Note that the realizing worst model might be different for each policy. This implies that the optimal non-robust policy, when evaluated using the respective worst model in the uncertainty set, can be very bad. This was shown in Kishan's previous work in AISTATS 2022. It is known that there exists at least one optimal deterministic Markov policy under SA rectangularity condition. We can then restrict ourselves to the deterministic non-stationary policy class. Similar to the non-robust case, we have the robust Bellman equation, with which we can calculate the optimal robust policy. In addition, we also have the robust Bellman consistency equation, which is not included here, but you can find it in our paper. It can be shown that the robust Bellman operation also enjoys the contraction property. In addition, the robust infimum operator L has nice Lipschitz property, which later will be used in a part of the proof. Analogous to the non-robust value iteration, we can perform backward iteration using these two, if we know the uncertainty set exactly. But how to find the robust optimal policy when the uncertainty set P is unknown? It is infeasible to generate samples from all P in the script P. We are interested in the algorithm that only assumes access to a generated model, which can generate samples only according to the nominal model P naught. Note that this is not the same as knowing the nominal model outright. The solution is we use a generated model to approximate the P naught and then construct the script P hat, which in turn approximate the uncertainty set P itself. In particular, for all HSA pair, we generate n next state transition samples. NH SAS prime is the number of transitions to state S prime in the n samples. Then we have the MLE estimate given by simply the sample average. And the construction of the empirical uncertainty set is straightforward. Here is a pseudocode which summarizes the idea. Note that step 5 and 6 are performing the empirical robust value iteration. The main focus of this paper is to characterize the sample complexity for this learning scheme. That is, how many samples from the generated model do I need before I can learn a robust value function that is epsilon away from the optimal robust value function. As you can see in the table, our results are uniformly better in terms of state dependency across all uncertainty set types. In addition, our bound enjoys the full gap between value functions, that is, epsilon can be anything between 0 and h. This is desirable because value function is bounded between 0 and horizon factor h. I will now go through the proof idea briefly. We can split the suboptimality gap into two terms. To bound the first term, we use the Lipschitz property of the infimum operator L. We can show that the gap between optimal robust value function and the output of RPVL at time h is upper bounded by this quantity at time h plus 1, and the error from approximating the uncertainty set P. Unrolling the recursion, we get that the first term is upper bounded by this quantity. To bound the second term, we use the robust Bellman consistency equation and the definition of the empirical robust value iteration. We can show that the gap between robust value of the output of our RPVL and the estimated robust value of RPVL at time h is upper bounded by this quantity at time h plus 1. Plus, again, this term. Similarly, the recursion gives us that the second term is also upper bounded by the same term, h times max HSA, and the approximation error. We are left with bounding the approximation error. This is the main challenge because of the nonlinear nature of the infimum operator L. Note that V hat is random. To provide any bound, we need to cover all possible VH. Again, due to the nonlinearity of L, infimum operator L, we cannot directly apply concentration inequality. Previous works have used uniform covering on the bounded value function class. This incurs the extra state factor in their sample complexity bound, because the dimension of your value function will come into picture. So our improvement is using proposition 1, which is a dual reformulation of the infimum operator. You can find different dual reformulation with respect to different uncertainty set distances in our paper. And using this proposition, we can show that for any fixed V, we can rewrite the approximation error terms in this way. The second term can be, this is the special case for total variation distance. The second term can be easily handled by Hofting inequality. The first term tells us that essentially we only need to cover the class of the form uv eta, and this is the vector of all ones minus v, and the subscript plus is max between 0 and the value. And eta is the dual variable. This is a much less complex function class than the script v, which is the general function class with all possible value functions. We can also show that the script n defined in this way is a theta cover for this function class, and its cardinality is just upper bounded by 2h over theta. Note that this cardinality doesn't depend on the state space size. This saves us the state factor in the complexity bound. For more proof detail, please refer to the supplementary material of our paper. Here, I will include an interesting simulation that studies the behavior of the robust policy. Imagine you walk into a bar and someone wants to bet with you. He will flip a coin. If it's a head, then you win the bet you choose. Start with $1. You can always bet whatever you have in your hand, but at most, the amount that can make you win the game in one shot. That is, say, getting $50 makes you the winner, and you have $30 in hand right now. At most, you can bet 20. Now you have a hunch that the guy is a cheater. He will swap out the nominal coin, which is something with something rigged, but not some coin ridiculously different from the promised coin. So the risk is still sort of like contained, and this is basically simulating the sim to real gap. The question is, what is the best strategy here? The training P naught is essentially the heads-up probability of the nominal coin. When the training P naught is less than 0.5, there is a family of optimal policies that achieve a winning ratio that equals to the testing pH. And both the non-robust dynamic programming and RPVL algorithm find such strategy as shown in the first plot in this figure. However, when P naught is greater than or equal to 0.5, there is a unique non-robust optimal policy that is simply bet $1 at each coin flip. This explains that when the testing pH increases, the winning ratio increases fast for the non-robust optimal policy, and hence it has an S-shaped curve. On the other hand, for all the robust policies with rho equals to 0.2, the uncertainty sets contain adversarial models with pH less than 0.5. Thus, all four robust policies still learn the conservative betting strategy as shown in the second plot in figure 2. Next, when the training P naught is 0.7, an uncertainty set with radius of rho 0.2 may or may not include the adversarial model with pH less than 0.5, depending on how it measures the distance between probability measures, and hence produces policies behaving differently, as shown in the third plot. Lastly, in the fourth plot, since the uncertainty sets are centered way beyond pH equal 0.5, all four robust policies converge to the strategy used by non-robust optimal policy. This tells us an important characteristic of robust policy. If uncertainty set is well designed so that it includes meaningful adversarial models, then the corresponding robust policy will manifest robustness. This will conclude my talk. Thank you so much.